Well, hello there. This is chapter 2 of the Radiographic Physics and Imaging book, Structure of the Atom, and this begins on page 16 of your book. All right, when we look at the structure of the atom, it's important for us to understand that in looking at radiologic science and understanding the physics of how things work in the tube and in the body and how the image is created, we have to have a good understanding of the atom. Now, why do we need to? Typically, when we talk about the interactions that take place in the X-ray tube that produce the X-rays, they actually occur at the atomic level, and the nature of the X-ray photon that gets produced depends on how an electron actually interacts with the atom, whether it interacts with the electrons on the orbital shell, or it's actually a degree of attraction between the electron and the nucleus. And that'll make more sense as we go. So we're just going to start with a fundamental understanding of the structure of an atom and how it's composed and what kind of things make up that atom. Also, when we talk about the interactions between the X-ray photons and the body, those occur at the atomic level as well. And based on those interactions, it determines both the radiation dose that's given to the patient and how the body part will actually be imaged, meaning that when those interactions take place in the human body, it determines if the part is going to show up on an X-ray because it's radiopaque and the photon gets absorbed in the part, or if it's not going to really show on an X-ray because it's so radiolucent that the photon passes right through. So those interactions take place at the atomic level as well. So understanding this is key. And then also, like I mentioned before, when we look at the interaction between the X-ray photon that leaves the patient and actually produces the image, that interaction takes place at the atomic level as well within the image receptor, and that creates our final radiograph or our final image. Okay, so having an understanding of the atom is vital. And they reference that other areas in our field also require a work knowledge of the atom. Now, as far as the historical overview, I'm not going to go heavy into that. Realize that Dmitry Mendeleev is the one that actually came up and organized the periodic table of elements. When he organized that periodic table of elements, he began with 63 elements total. That periodic table of elements is actually on page 23 of your book. And in 1869, Mendeleev actually put this together with 63 original elements, and he came up with these groups, these periods, and they were organized in such a way that as new elements were discovered, whether they were naturally occurring or they were created, man-made, they actually fit into his original design. So we'll look at that a little bit later on, but just know that Mendeleev is the one that actually created or organized the periodic table of elements. This occurred in 1869 with 63 original elements when he first started that. Okay, and when we look at the modern theory as far as the atom, Niels Bohr is typically who we focus on because he's the one that kind of gave us the final look that in statements that atoms have three fundamental subatomic particles. They are composed of electrons, neutrons, and protons. And the quantity of each of those is unique to the matter or to the element that it makes up, meaning different elements have different number of protons, different number of neutrons, different number of electrons. And Niels Bohr is also the one that that reference that these atoms are in constant motion. Okay, so when we draw it like it shows on this slide right here, everything is flat, just two-dimensional, kind of laid out, no motion to it whatsoever. But in reality, when we look at an atom, it's constantly in motion, and that's what makes the interaction so unique, is because you don't really know where you're interacting when it occurs. And I will show you that in a separate video that I'll record to kind of show you what I'm talking about with that. But just realize that each quantity of each of these subatomic particles definitely is unique to the element that it composes or makes up, to the matter that it's made up of. Meaning a hydrogen atom is completely different from a lead atom. That is completely different from a tungsten atom or a carbon atom. In any of the atoms we look at, as long as they're different elements, then there is a different number of electrons, protons, and neutrons. And we'll look at some of those elements when we get back to the periodic table. When we look at an atom, again, realize that the nucleus is made up of protons, which have a positive charge, and neutrons, which have no charge. They're neutral, okay? And the bulk of that nucleus, while an overall positive charge, the amount of protons and neutrons actually make up the atomic mass. And when we look at the protons and neutrons collectively, we call those nucleons. Nucleons. The protons and neutrons together in the nucleus are made up and collectively referred to as nucleons. And that is found on page 18 of your book, where it references that the atom has a nucleus made up of protons and neutrons, collectively called the nucleons. And then orbiting the nucleus are electrons in defined energy levels, or what we call orbital shells, and they are a specific distance from that nucleus. Okay, so when you have the nucleus, typically the first shell beyond the nucleus is your K shell, your L shell, then your M shell, and it continues as far as you go out, however many shells you would have. The protons. When we look at the protons electrically charge-wise, they're positive. Neutrons are neutral, meaning they have no electrical charge. And electrons, like we said, are negative. And when we look at those, remember the protons and the neutrons are found in the nucleus. Those are referred to as nucleons. And the electrons are actually found on the orbital shells outside of the nucleus. All right. When we look again at the electrical charges, speaking of protons having a positive charge and neutrons have no charge and electrons have a negative charge, electrical charge is a characteristic of matter. And remember, matter is anything that has mass, occupies space, and has shape. Okay, so has mass, occupies space, and has shape. That is considered matter. Typically, when we refer to matter, we're usually speaking about the patient. But electrical charge is a characteristic of matter, whether you're talking about a subatomic particle or an atom or a larger object. So always, each proton has 1 unit of positive charge. Each electron has 1 unit of negative charge. And neutrons are neutral, so they have no charge at all. When they talk about an atom, if there are an equal number of protons and electrons, then it would have no net charge, meaning I'm going to show you this in another video, but if you imagine that an atom has 6 protons and it has 6 electrons, it means it would have 6 positive charges and 6 negative charges. So each of the positive would have a negative to counteract it or knock it out, make it neutral. So when there's an equal number of both, then it ends up being a stable or a neutral atom. If you disrupt that balance, then the atom will gain an overall charge. So if if you disrupted the electrons and you ended up with more protons than electrons, you would have an overall positive charge. So if you had more protons than electrons, you would have an overall positive charge, and that is called a positive ion, or another term that they use for that is a cation. I'll try and write that for you. So when you have a positive ion, it's also called a cation. C-A-T-I-O-N, a cation. Okay? If you had more negative charges than positive charges, you would have an overall negative ion. And a negative ion can also be called an anion. A-N-I-O-N. So a positive ion can also be called a cation, and a negative ion can be called an anion. All right. So either way, if you lose an electron or you lose a proton, you've ionized that atom, meaning that you've caused gain or loss typically of an electron. And if you gain or lose an electron, you have ionized that atom. And if you remember, ionization is the process that X-rays can cause, and it makes what we do potentially dangerous, meaning we have the ability to disrupt atoms at the atomic level. So we have the ability to ionize matter. We can cause cations and anions in a patient. Now, why is that a big deal? Because we've talked before that if you disrupt that atom or that cell and it ends up being in a mitotic state, then what can happen is that when that cell reproduces in a mutated or in not the same state that it was, then what you end up with is cancer. Okay, but then when you get cancer, we basically send you to radiation therapy and increase the energy, and we target that cancer and we kill it. All right, so we do have the ability to ionize atoms with the X-rays that we take of patients. Now, continuing on, looking at the nucleus of an atom. The nucleus is actually held together by a strong nuclear force that creates a binding energy. Okay, so in the nucleus, there's a very strong attraction that actually can overcome the natural tendency for the like charges to repel. Remember, one of the laws of electrostatics is that like charges repel each other, unlike charges or opposite charges attract. Okay, so like charges repel, opposites attract. That is a law of electrostatics. So it doesn't really make sense in the nucleus when you think about all those positive charges and the neutral charges. Why don't all the positive charges repel each other? That is because of the nuclear binding energy. So there's a strong force in there that actually overcomes the need to repel each other, and they actually stay together. So it holds the protons and neutrons together to form the nucleus. And then you also have binding energy, is what holds together. Binding energy actually holds the electrons on the orbital shell. But before we get there, it says that it creates a strong attraction in the nucleus, overcoming the natural tendency for like charges to repel. It holds the protons and neutrons together to form the nucleus. It also is a measure of the amount of energy that you would need in order to split an atom. Okay, so binding energy measures the amount of energy necessary to split an atom or break it apart. And if a particle actually strikes the nucleus with energy equal to the nucleus binding energy, the atom could split. All right. So the nuclear binding energy, it is possible to overcome that and actually break that nucleus apart. when we look at the electrons, we said that they orbit the nucleus on the orbital shells or on the electron shells. So they orbit the nucleus at very, very high velocities. And the electrons are actually held in their orbit by electron binding energy, meaning that the negative charge of the electron on the shell and the positive charge of the nucleus from the protons, those opposites actually attract. Okay, so the fact that the opposites attract, it also has a part in, it depends on how close the electron is to the nucleus and how many protons are in the nucleus. So if there are a significant number of protons in the nucleus, it's got a very strong positive charge. So the electrons that are on the closest shell to the nucleus, which is K shell, the degree of attraction between those is going to be much stronger than the electrons that are further out on the orbital shells. If you had, let's go back to that one picture. So if we look at this picture of the atom, and you've got this positive force in the nucleus, and these are all negative, the degree of attraction between this positive and this negative is much stronger than the degree of attraction between the positive and this negative. Why? Because they're further apart. Think about if you were holding a magnet and you were holding them closer together, then ideally the closer you hold them together, the stronger the degree of attraction. You can feel the pull between your fingers. But if you were to pull those magnets further apart, it doesn't mean that there's still not a degree of attraction, but it might be so weak that you're not able to actually feel it. So the same thing happens on the orbital shells of these atoms. Okay, so the electron binding energy is determined by how close is the electron to the nucleus, and then how many protons are there in the nucleus of that atom. So the closer it is, the stronger it is. The farther away, the weaker it would be. All right, so nuclear binding energy and electron binding energy are key determinants of X-ray production, meaning the nuclear binding energy determines one interaction that takes place in the tube, and the electron binding energy plays a part in another interaction that produces X-ray photons in the tube. So in the X-ray tube, we have two types of atomic interactions that produce X-rays. We have characteristic interactions and Bremsstrahlung interactions. Okay, and we go into these in much more detail at the beginning of week 2, but I will tell you that the characteristic interaction is the one that is determined by the binding energy, the electron binding energy, and the nuclear binding energy determines the Bremsstrahlung interactions that take place. Okay, so in a characteristic interaction, typically you're removing an orbital electron from an atom, and in a Bremsstrahlung interaction, you're not removing anything. It's actually a degree of attraction between the incident electron and the nucleus. Okay, and if I lost you on that, it's okay. We will get back there. If I didn't completely lose you, then maybe play that over a couple times and listen to what I'm saying, and it might help make sense. So these two interactions, Brems and characteristic, make up the photons that are found in the primary beam of the X-ray. So when you make an exposure, what comes out of that tube is called the primary beam. And the photons in that primary beam come from these two interactions, both characteristic interactions and Bremsstrahlung. Will you be able to tell the difference between the two by looking at the X-ray tube? Absolutely not. You would have to really understand what took place in order to create those photons to truly understand that, but it's not something that you can visualize. When we look at the atom, it has defined energy levels, and each of those energy levels are at a different distance from the nucleus, and this is called our electron shells. Okay, this makes the rings around the nucleus. This is where the electrons sit, is on the electron shells. So they each have defined and different energy levels. And remember that electrons actually orbit three-dimensionally around the nucleus. So if I was trying to draw this, all right, and if we have our nucleus in the middle here of an atom, okay, if you have a nucleus, and then we go ahead and give it some orbital shells, realize that when you give it orbital shells, they're in motion around the nucleus. Okay, so it kind of looks like, you know, at the beginning of Big Bang Theory where they have the atom, and this is in constant motion, meaning this is moving all the time. It's not nice and flat like we typically draw the nucleus, and then K shell, L shell, M, N. It's not like that. Like on page 18 in your book, it's not nice and flat and laid out. It's actually three-dimensional. Okay, so they orbit three-dimensionally around the nucleus. Each electron shell is numbered or lettered. Typically it begins with letter K, which is closest to the nucleus, and it moves outward in succession. So K is the first shell, L is the second shell, M is the third shell, N is the fourth, O, P, and so on. Okay, and the shells fill from the K shell outward, even though the outermost shell may not completely fill. Each shell has a limit as to how many electrons it can actually hold, and you can calculate that number by using the formula 2n squared. And n actually represents the shell number. So like K would be shell level 1, L would be shell level 2, M would be shell level 3, and so forth. So if you took the formula 2n squared, that would actually tell you the maximum number of electrons that a particular shell could hold. And I will show you that in a separate video where I actually use the whiteboard and show you exactly what I'm talking about with that. As for the outermost shell, typically they do not have they are not full with electrons. Typically, the number on the outermost shell is varying, and it actually determines whether that atom will bond ionically or covalently with another element. So even though the shells can hold a certain number of electrons, they're not necessarily full. K shell typically is full because it can only hold 2 electrons, but on an outermost shell, typically a maximum of 8 electrons can exist in the outermost shell of any atom, and that is called the octet rule. Some of the inner shells can actually hold more than 8 electrons, okay, like K holds 2, L maxes out at 8, M actually maxes out at 18. And again, I'll show you that. So 2, 8, 18, N can hold 32. O can actually hold 50 if it had that number of electrons to be able to do that. It says if there were more electrons present, though, with the M shell holding 18 and you had more, they would actually fall over into the N shell, meaning M can't exceed 18. So if there was some left over, they would go on the N shell. All right, so the outermost shell of an atom can hold less than 8. It could hold 8, 7, 6, 5, 4, 3, 2, or 1, but it could never hold more than 8 electrons, and that is referred to as the octet rule. And that is actually found on page 20. Okay, and they reference that it's important to note in the right-hand column that the outermost shell may hold fewer but no more than 8 electrons. All right. When they look at an atom, it almost looks like a target for interaction. Okay, if you think of the nucleus more like a bullseye, and the electron shell levels are your actual rings. So if you were doing archery or shooting of some sort, that literally looks like a bullseye with all the different rings, and typically the scores are different depending on where you hit. All right, so when we're talking about atomic interactions in the X-ray tube, the atoms represent the target. If you're talking about how you interact with the photons in the X-ray beam with the human tissue, that is a target for interaction as well. So it always is going to be thought of like this, but again, the only thing we want to remember is this is only representing 2 dimensions. Drawing it nice and flat with the nucleus in the middle, orbital shells outside the nucleus, and everything is nice and flat and no motion through it whatsoever. So this is just a good book representation. This is not what it would look like. It would be in motion constantly. Okay. They reference that there's more opportunity for interaction with a large atom because typically the nucleus is larger and there's more electron shells and more electrons are in orbit around the nucleus. There's less opportunity if you had a very small atom because the nucleus would be much smaller in size because it would hold fewer protons and neutrons, and it would have fewer shell levels with electrons on it orbiting, so less likely to be hit or struck and interact with. All right. As far as classification and bonding, recognize that there are a few things we have to understand about the atoms and some of the definitions. The first thing they talk about is the atomic number of an atom. Okay, so the atomic number is always referring to the number of protons in the nucleus. Okay, so if you had 6 protons in the nucleus, you would have an atom of carbon. If you had 8 protons in the nucleus, it's an atom of oxygen. If you had 42 protons in the nucleus, it's an atom of molybdenum. If you had 74 protons in the nucleus, it would be an atom of tungsten. So the atomic number represents the number of protons in the nucleus. And if you have a different number of protons, then you absolutely have a different atom, a different element. All right, so 6 protons is always going to be carbon. 74 protons, always going to be tungsten. Okay, so the number of protons in the nucleus is the atomic number, always. The atomic mass number is always the sum of the protons and the neutrons in the nucleus. So when you have the atomic mass number, it's always the total of the number of protons and neutrons in the nucleus of an atom. We'll use tungsten for an example because that's one we always have to know. When we look at tungsten, it has 74 protons. It has 110 neutrons. So the atomic mass of tungsten is 184. Truly, it's like 183.84 or something like that, but we can round it off to 184 and just call it that. So 110 neutrons, 74 protons in the nucleus of a tungsten atom. Typically, when we talk about elements, They are the simplest forms of substances that make up matter, and each element is made up of only one unique type of atom with an unchanging number of protons. So the number of atoms that make up a molecule of an element varies. There are 92 different elements that are naturally occurring, and all the rest have literally been man-made or artificially made. Okay, so when we look at the periodic table, which is coming up in just a minute, 92 of those are naturally occurring. The rest are all man-made. All right, when we look at a molecule is made up of two or more atoms bonded together. Okay, so molecules, two or more atoms bonded together. When we talk about naturally occurring elements, typically you're talking about when they're naturally occurring in nature, they're pure, they're not combined with other elements. So you're talking about things like iron, zinc, nickel, oxygen, carbon, hydrogen. All of those are pure, naturally occurring elements. When we tend to look at everything around us, though, typically it's in some form of a chemical compound, which are combinations of the elements bonded together. Okay, like when we look at water. When you look at water, it's actually two atoms of hydrogen and one atom of oxygen, because typically when we think of water, we think of H2O. Okay, so two atoms of hydrogen, one atom of oxygen is water, H2O. So a molecule is two or more atoms bonded together. A compound is a combination of elements bonded together. And then the last part, when we look at this chemical symbol, just to understand, when we look at the periodic table of elements, it's an abbreviation of the actual element. So when we look at that, whatever the symbol is typically in the middle of the square. You have somewhere referenced the Z number is the atomic number, which remember that's the number of protons in the nucleus. And then you have another number which represents your atomic mass number. And remember that's the number of protons and neutrons in the nucleus. Now, on page 21, they talk about all these classifications called the isos, and they reference isotopes, isotones, isobars, isomers, and basically it's a way to classify the relationship based on protons, neutrons, and electrons. Now, the only one we're going to concern ourselves with, and that is why I put it in red, is an isotope. Okay, when we look at isotopes, an isotope is where an element has the same number of protons, but a different number of neutrons. Okay, so the weight, the atomic mass would be different, even though it would be the same element. Okay, so an isotope has the same number of protons, different number of neutrons. Hopefully that makes sense. We tend to look at isotopes, or we use isotopes in nuclear medicine. Sometimes they will use technetium-99. There's one, I believe, for iodine, but what it means is it's the same element, has the same number of protons, but the weight of the element is slightly different. So isotopes are the only ones we really concern ourselves with. Not to say that isotones or isobars or isomers are less important, but as far as radiology is concerned, isotopes are really the only ones that we deal with. Now, the periodic table of elements. I put this one in. I know it's a little bit small, a little bit hard to see, but I will tell you that I prefer this periodic table of elements to the one in your book, because if you look at the one in your book, it actually only lists 114 elements currently, and I can tell you that to date there are 118 so far. So if you look right here, this number right here is 118. In the book, it actually stops with number 114, and if you look in the book, the one that's 114 is actually labeled UUQ in the book. And if you look here, it actually has a name. Let me try and zoom in here and see if I can. Well, let me zoom long enough to read it. But 114 here actually has been named since this book since your book was published. There's actually a name given to that now, which is interesting. When we look at this periodic table of elements, remember I said that Dmitri Mendeleev is actually the one that came up with this in 1869 with 63 original elements. He grouped these together. Okay. What he came across and realized and how he set it up, that each group or column, which means from top to bottom, these all have the same number of what are called valence electrons or outermost electrons when they go by groups or columns. When you go across, this is considered a period or a row. So from side to side, each of those have the same number of orbital shells. So let's use tungsten for an example. Tungsten is right here, number 74. Tungsten has 6 orbital shells, K, L, M, N, O, and P. Everything in this row has 6 orbital shells. Okay, so everything that's been added to this, what Mendeleev started, is still in existence today. All right, so organized by periods and groups. It says there's 7 periods, which means side to side. So 1, 2, 3, 4, 5, 6, 7 periods. And there are 8 groups or 8 columns. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so those are the groups from top to bottom, and side to side, those represent the periods. Okay, so the atoms in each period, meaning from side to side, have the same number of electron shells. And it says the number of shells increases as you move from the top to the bottom. So meaning this right here, hydrogen and helium, have 1 orbital shell. This row, 2 orbital shells, 3, 4, 5, 6, 7 orbital shells. Right? And in each group, from top to bottom, meaning 1, 2, 3, 4, 5, 6, 7, and 8, in each group, they have the same number of electrons in their outermost shell. That's called your valence electrons. Right? And the number of electrons in the outermost shell goes from 1 in group 1, so all of these have 1, these have 2, 3, 4, 5, 6, 7, and 8. All right, and they do reference that the periodic table is not perfectly uniform because in the middle of the chart we have all of these elements that don't really fit into those periods and groups. These are called your transitional elements or your transitional metals. All right, all these yellow ones right here you can see, these are your transitional metals. And these have different characteristics than the rest. And there's other ones that don't fit into the groups either. These down here are your inner transitional metals. This is the lanthanide series and the actinide. Now, am I going to go into this all with you on your test? No. I would love for you to know that Mendeleev came up with it in 1869 with 63 original elements. I want you to recognize that from top to bottom right here, this being 1, 2, 3, 4, 5, 6, 7, and 8, those are our groups or our columns. And from side to side, starting with hydrogen 1, 2, 3, 4, 5, 6, 7. Those are your 7 periods or rows. Okay, now I am going to give you some elements that I expect you to know the name of and the number of. Now, if we look at this, you probably want to highlight them in your book, but I'm going to tell you what ones we need to be mindful of. First one is hydrogen. Hydrogen is number 1. So anytime you have atomic number 1, you always have hydrogen, meaning hydrogen has 1 proton. So that's the first one you need to know. Then we'll come over here. We need to know carbon, number 6, nitrogen, number 7, oxygen, number 8. You also need to be mindful of number 13, aluminum, number 20, calcium, 26, iron, 28, nickel, 29, copper, 42, molybdenum, 45, rhodium, 47, silver, number 50, tin, number 53, iodine, number 56, barium, number 74, tungsten, 75, rhenium, 79, gold, 82, lead, number 90, thorium, and number 101 is mendelevium. Okay, so all of those atomic numbers that I gave you, I need you to be mindful of the atomic number and what element does that represent. The only one that we need to know more than that about would be number 74, tungsten. And we'll go into that in more detail on the other video. Okay, so make sure you highlight those in your book so that you're mindful of what atomic number that is and what element it represents. So that if I said to you, what's number 6, you would say carbon. Or if I said, what is number 75, rhenium? Or if I said, what number is thorium? You would tell me 90. Okay, that's what I expect for you to know on that periodic table. Also, who came up with it, when, how many original elements, what's a period, and what does that represent, and what's a group, and what does that represent. Bonding is the last portion that we'll talk about, and there's 2 ways that atoms can bond in order to form a molecule. Okay, they form a molecule in other structures, but one is called an ionic bond, and the other one is a covalent bond. So if we look at the ionic bond first, typically ionic bonding is based on the attraction of opposite charges. Remember that most atoms are neutral, meaning they have the same number of protons as they do electrons. So when they have an equal number of positive to the negative, they all cancel each other out, and it makes the atom neutral or stable. It says, but sometimes in the presence of other atoms, they'll have a tendency to give up electrons, and some will have a tendency to gain electrons. So an atom that gives up an electron would then have an overall positive charge because it would have more protons than electrons. And remember, that's called a cation. And an atom that gains an electron, meaning now it has one more electron than proton, would have an overall negative charge called an anion, or it could be called a negative ion. But a negative ion is called an anion. So when you have an ionic bond, one of the atoms gives up an electron and the other one takes the electron. And then the difference in their electrical charges actually attracts and bonds them together, because remember, opposites attract. So when this one is positive and this one is negative, those two attract to each other. Okay, so they have an electrostatic attraction, and the element, the compound they're showing you here is NaCl, or sodium chloride, which is salt. Right, so you can have ionic bonds where something gives up and one other takes. And then we have covalent bonds. And covalent bonds, the easiest way to think of that is that they share. They play nice in the sandbox. So pretty much what happens is two atoms will actually share electrons that orbit both nuclei. All right, so it says an outermost electron from one atom begins to orbit the nucleus of another in addition to its own original nucleus, and it kind of creates that figure 8 pattern. So in a covalent bond, typically you refer to that as sharing. Okay, so ionic, it's giving up something. Covalent, it is sharing. And that's how things bond together to create things that are bigger than atoms, like our compounds, our molecules, our organs, our organ systems, the organism, meaning us as humans as a whole. We're made up of all these atoms, but they come together to form skin, organs, your liver, your spleen, your kidneys, all your different parts, and ultimately to form the organism. So we start at that very basic atomic level and continue up from there. Okay, that brings us to the end of this. Now recognize that this was simply lecture from this chapter. I think it would benefit you to actually look at the other video. And what this other video is going to show is I'll actually go through some of this and explain a little bit better, let you visualize what I was talking about what an atom actually looks like, as far as, you know, being in constant motion. We can look at the fact of if an atom is ionized and gives up an electron. And we can actually look at the entire part of a tungsten atom, because that is the one that you are responsible for knowing everything about a tungsten atom. Okay, everything else that I gave you as far as an atomic number, I'd like you to recognize the number and the element that that number represents. But as far as tungsten, which is number 74, we're going to look at everything about that, because it comes into play when we talk about interactions that take place in the tube. All right, that concludes the lecture from chapter 2. If you have any questions or any confusion or comments, please go ahead and write that down. And when we meet again, hopefully I'll be able to clear that up for you. Thank you so much.